Hello and welcome to this presentation from Diodes Incorporated, in which we will be having a look at some motor driving solutions. My name is Isaac Simpson and I'm the Automotive Applications Engineer covering North America and Europe. So let's get into it. As we go through this presentation, we will have a look at what the target markets for Diodes Inc products in motor driving applications are, take a more detailed look at what is needed to drive DC motors, and take a look in turn at some various Diodes Inc solutions for this application area. If you have any questions or queries arising, please contact your local Diodes Inc representative. So a simple statement of the target markets for Diodes Inc products in driving DC motors is we're looking at the power level up to about 2 kilowatts, both brushed and brushless. And the reason for this positioning is simply to do with how it aligns to our portfolio. In terms of voltage, we have a strong portfolio of Mosfets and gate driver parts up to 100 volts, and that enables solutions up to 48 volts in an automotive context, 60 volt parts for 24 volt solutions, and 40 volt parts for 12 volt solutions. We have a wide variety of Mosfets in different packages, and capable of up to over 100 amps, and aligning this area in terms of the MOSFET capability and the voltage capability gives us that power level up to about 2 kilowatts. And this is based around silicon MOSFETs at this point in time. We are working on silicon carbide, and that will come in the future, and we will update you as we have more to share at the time. So thinking about some applications for DC motors up to 1 to 2 kilowatts outside of the automotive context, and we can think of an enormous number of uses for such motors. This is by no means an exhaustive list, and there are many other applications, but you can see that there's a huge number of domestic requirements in terms of appliances, laundry, dishwashers, etc., refrigeration, the compressors required, coffee machines, coffee grinders, blenders, mixers, vacuum cleaners. And if we take vacuum cleaners as an example, we are seeing a huge shift now away from the classic upright or separate vacuum cleaner that plugged into a main socket to handheld battery-powered devices. And in fact, we may see an increase in the number of motors here, because we're now seeing separate motors to drive a brush bar as to the one that drives or pulls the air through the system. Sticking in a sort of domestic context, a lot of pumps, boilers and heat pumps, domestic HVAC systems, etc., and the number of motors there increases over time. In Europe, certainly a move towards air source heat pump heating systems to replace gas boilers means you need a number of DC motors to drive fans, to drive compressor motors, solenoids to redirect flows, things like that. There's also a huge number of recreational uses for DC motors at this kind of power level, things like e-bikes and scooters, drones, computer gaming, and many other applications. If we look into the automotive context, and even quite apart from the electrification of the drivetrain of the car, we are seeing an increasing number of electric motors as a default in all cars. 15 to 20 years ago, you could easily buy a car that had manual windows and manually adjustable door mirrors, whereas now, even at the very bottom end of the market, these things are typically electric. And this kind of shift of the default specification means that there's a greater requirement for motors across all vehicles. If you look at a mid-range executive sedan, again, 15 years ago, you could well have had one with manually adjustable seats, whereas now the base specification is likely to at least include partial electric movement of the seats. Things like doors, windows, etc., there's the increasing amount of comfort requirement for motors in vehicles. However, we're also seeing a significant shift away from mechanically driven items in the engine. So moving power steering, aircon compressors, water pumps, oil pumps, etc., away from being mechanically driven to being electric motors. Moving the brake booster servo away from being driven by the engine to being electrically driven so that it remains functional during stop-start, that kind of thing. So there is a shift to more and more electric motors in this power range in every single vehicle. A lot of marketing materials would have you believe that the brushed motor is dead and will be completely replaced by brushless motors in all applications. This is simply not true. Brushed motors have their advantages in terms of low cost and simple control. They're perfectly reliable enough for a lot of functions where they're only used occasionally. Let's consider something that we mentioned on the previous slide of a door mirror movement. Only requires a small motor to drive it. And once you've set the door mirrors on your car and saved them to where you want them to be, you don't tend to use that motor again for a very long time. But even if your car has a function whereby the mirror dips down so you can see the curb as you're reversing, even if you use that twice a day, then the motors may be moving for 20-30 seconds in a day. If it moves for 20 seconds in a day, that's about 2 hours of use in a year, 20 hours of use over a 10-year lifetime of a car. It's simply not necessary to put in something reliable for tens of thousands of hours that you are maybe going to use for a few tens of hours over the lifetime of the vehicle. So the brushed motor is a very, very good fit to a lot of these small, rarely used movements in a vehicle, or where the cumulative lifetime hours of the motor are never going to be desperately high. And that includes seat adjustments, door mirrors, steering column adjustments, pop-out cameras, that kind of thing, tailgates, and so on. That's not to say that brushless motors are unnecessary either, because there's plenty of applications where brushless motor advantages are key in terms of reliability, in terms of efficiency, in terms of smoothness. So where you have the HVAC fan in a car, for example, this is going to be running constantly the entire time the car is used. So it's going to be running for 1 to 3 hours a day on average. So 1,000 hours a year, 10,000 hours over that 10-year lifespan. So these are things where we definitely do need that kind of reliability and lifespan. And especially when we are talking about things that start to impact on functional safety, such as power steering, coolant pumps, and parts of the drivetrain. So there is room for both brushed and brushless motors. So let's take a look at how we actually start to drive some of these motors. And let's start simply with a brushed motor that we want to drive in one direction. We can represent the motor coil as an inductor here. If we simply want to drive it in one direction and never ever switch it on or off, all we need to do is apply power through it, have a current flow through it from positive to ground. Obviously, this isn't necessarily very useful because typically we want to be able to control a motor, both in terms of being able to switch it on and off and also regulate its speed, which we do by switching PWM, and we need a switching element for that, and that's going to be a Mosfet. And hopefully, if you're paying attention, you'll recognize that any situation where you have an inductive load like this that you're switching on and off, you are going to need flyback. If we consider the case where we want to drive a brushed motor in more than one direction, so going back again to that door mirror where we want to be able to drive it up or down, left or right, then we need to be able to change the direction of current through the coil. And typically we'll do that using an H-bridge configuration like that shown. If we switch on the appropriate combination of MOSFETs, we can drive the current in one direction through the coil, and if we switch those off and switch on the other two, then we can drive it the other direction through the coil. This also allows us to drive a single-phased brushless motor, where we need to handle the commutation of the coil externally. And that's typically done by a motor driver chip or a microcontroller, and that'll be driving the MOSFETs in turn, commutated either by a Hall sensor or by sensorless methodology. And that switching of the MOSFETs then replaces the copper commutator and carbon brushes typical of a brush motor. In order to be able to drive a brushless motor in both directions, we need to move to a three-phase architecture that allows us to modulate the phases in a different order in order to generate rotation in one direction or the other. In order to drive this electrically, it's very similar, but we need a third half bridge to drive two more MOSFETs to drive the current through the different phases in turn. And you'll be able to see how that works in the animation following. So having seen the different ways of connecting up the different types of motors to the MOSFETs, we'll take a look at the more general block diagram for any motor system. And where we have the power come in from the left, there will always be some kind of power input protection, certainly in an automotive context. And that will take the form of TVS devices, a reverse polarity protection, which could be just a simple rectifier device, a P-channel MOSFET, or an N-channel MOSFET with an ideal diode controller. Then you have the MOSFETs forming the bridge to drive the motor itself, but the MOSFETs will need some kind of level shift and current buffer in order to be driven from a micro or driven from a low-level signal. And that can take the form of discrete transistors or gate driver devices, and that would include functions like generating an above rail voltage to switch a high side N-channel MOSFET. You may also need some Hall sensors in the motor, and these are all parts that Diodes Inc. can supply. One useful device here is the DGD05473FNQ gate driver. This is a 50 volt floating high side driver, which is a high side low side gate driver allowing independent control of the two MOSFETs connected to it. This can source 1.5 amps and sink 2 amps, so it's capable of driving significantly higher current into and out of the MOSFET gates than a microcontroller would be able to. So this is acting as the buffer, and it will generate the above rail voltage required to drive the high side N-channel device. As a Q part, this is automotive qualified, PPAP is available, everything is in place for automotive usage. When it comes to MOSFETs, Diodes Inc. has two particular strengths in our MOSFETs for these kinds of motor control applications. The first of these strengths is our packaging technologies. We have been a leader in leadless packaging and very small sizes, and in offering up some of the dual packages as well in some of these smaller devices. I still find it absolutely mind-blowing that we're offering 2x2mm MOSFETs that in the dual are capable of delivering in excess of 7 amps and the single over 11 amps from that small of a device. And so here we're suggesting some of the packages that we would use at different motor power levels, that the dual DFN 2020 is capable of supporting motors up to about 50 watts. Single DFN 2020 can provide power to a 100 watt motor, and obviously extremely small PCB space required there. The dual 3x3 remarkably up to 250 watts, and as you see we continue up 500 watts for single 3x3 or dual 5x6, and above that we are offering single 5x6, the 8x8 and the 10x12 toll package, and this will provide power for motors in excess of 1 kilowatt. Our second strength in MOSFETs is our MOSFET process and technology, especially the split gate family, offering a combination of low gate charge and low RDS on. So among the industry leading levels of figure of merit there. And these products cover a wide range, and so following on from the previous slide with the suggestion of power levels to packages, we can follow that down here, that we would start with some of the, even a complementary H-bridge device at the top, or a dual N-channel in the SO8 package, so that would be for motors up to about 25 watts, and then following on from the previous slide, some of the top pick parts that I would suggest for different motor power levels. I've mentioned the dual 3x3 and 5x6 devices previously, and one of the really nice things these allow you to do is to create really compact H-bridge layouts where you have simple, heavy islands of copper on the PCB layout, and this will give you the best thermals. You have limited the path lengths of the switching nodes, keeping everything close together, and basically maximizing the performance thermally, electrically, EMC characteristics, minimizing parasitics, and minimizing the board space required. For a three-phase system, we can make a similarly optimized layout with short path lengths and heavy copper areas, and again optimized thermals and EMC. This time by interleaving the MOSFETs, so that you can see here the motor 1 phase uses Q1B and Q2A. So the high side MOSFET in Q2 here feeds into the MOT1 phase and then down to ground through Q1B. Moving on to have a look at some of the solutions that Diodes Inc. are offering. We'll start with this, the DDB078, which is based around the DMHC4035 LSDQ, which is a complementary H-bridge device in the SO8 package. This is 40 volts, 2P, 2N, and it can deliver in excess of 3 amps to the load. For this, with the simplicity of driving the P channels on the high side, we simply needed some discrete buffering to provide the current drive and level shift from a micro, and that's implemented just using some simple bipolar transistor parts. There is a current sense resistor to provide current feedback to the microcontroller, and there is a DFLT28AQ TVS device on the power rail. So this would be ideal for, again, the door mirror that I keep coming back to. Simple bidirectional brushed motor control and very low cost, very compact. And all of the parts, semiconductor parts on here, are Automotive Q parts, PPAP available, and so this represents a ready-to-go solution to hook up to a basic micro. Our next solution is for a three-phase motor up to about 50 watts power level, and this is using the dual DFN 2x2 device, the DMN 3032 LFDBQ. This device itself can deliver over 6 amps. We've tested this board to outputs of more than 3 amps, so that would be good for something like a local zone climate fan within a vehicle, or small door opening, door closing, where somebody wants a brushless motor for smoother action. This uses the DGD05473 FNQ gate driver that I highlighted previously, and again there's a current sense signal from this PCB to feed back to the microcontroller that's driving it. Again, all semiconductor parts involved are Q parts, automotive rated, and so that's a ready-to-go solution, and demo boards are available. Moving up in size to the dual power die 5060 packaged MOSFETs, and now using the 60 volt DMTH 6010 LPDQ, we're offering up the DDB099 board, and this is good for 12 and 24 volt applications, and the parts are capable of in excess of 40 amps. The PCB itself should be good beyond 10, so it's offering up about a 200-250 watt solution using these parts. Again, this uses the same DGD05473 FNQ gate driver from the previous board, but in this case we also have 3 current sense outputs made available to micros in order to allow for sensorless commutation schemes. Again, all semiconductor parts are automotive grade Q parts on here, and so that would be good for a main HVAC fan or something like a smaller water pump or something like that. Using the same PCB, we can build using some different parts as well. So in this case now we have moved up to 100 volt FETs in the same package, the DMTH 10H017 LPDQ. And again, these are capable of currents in excess of 40 amps. And we've changed the gate driver now to the DGD0579U, which is also a 100 volt part. And that combination then will allow us to drive 48 volt applications. Again, up to about the same sort of current, so this should go probably pretty close to 500 watts rather than 250. 250 would be a very safe level for that. The only caveat to this at this point in time is that the DGD0579U is not currently automotive grade. So this is a commercial grade solution at this point in time, but we are hoping to come out with the development of the DGD0579 that will be automotive grade. I have made mention a couple of times of automotive compliance, and we offer a wide range of products that are automotive compliant in terms of being qualified to the appropriate AEC-Q standard, manufactured in IATF 16949 facilities, capable of VDA 6.3 customer audit, and supported by the appropriate documentation, PPAP, and change controlled. We identify these parts by putting a Q at the end of the part number. So if you are looking for an automotive solution, select Q parts and you will not have a problem getting the appropriate documentation. For distribution, a wide range of our products are design registrable, including many of the Q parts and the higher value MOSFETs and gate drivers. So if you're looking for design registration, then these are parts to go for, and then of course any other parts included within that design will be included within your design registration. This slide will give you some links to a few bits of further reading and more in-depth information on some of these techniques and some of the solutions that we are offering. If you have any questions on products or solutions mentioned in this video, then please contact your local Diodes Inc. representative, who should be able to help you or pass your query on to me or another of the automotive group. So with that, I would like to say thank you very much, and we hope to hear from you shortly.